Okay, this is Physics Chapter 13. This will be the third and final lecture for this chapter. We're starting on page 5 of your notes, and in the book we are on page 446. So up at the top of page 5 on your notes, there are a couple of places for you to write formulas in. And the first one is E, and it's a vector, okay, is equal to the electrostatic force over the moving charge, little q, okay? And this is the only formula in the entire chapter where you include the sign. So you include the sign for the force, you include the sign for the moving charge. All right, so that is what we'll call vector E. And we're going to use this formula as a shortcut to being able to calculate the force. And electric field, okay, so this is non-vector, is K times big Q over R squared. Big Q is the stationary charge, all right? The charge is fixed, and that's how we differentiate between a fixed charge and a charge that's allowed to move, little q, and we'll do that a lot in chapter 14. So let's look at on your own 13.8. All right, that one says 2 plus 0.4 millicoulomb charges are placed 2 meters apart. Calculate the magnitude and direction of the electric field at the point shown in the drawing below. All right, so I'll draw this out. All right, so we've got a plus 0.4, and that's millicoulombs. We've got a point in space there. And this one's also plus 0.4. Probably having a hard time seeing that, but if you're following along in the book, 0.4 plus 0.4. And the distance, between the total distance is 2 meters. The distance from that dot would be 1.6 meters on this side and 0.4 meters on this side. We'll call this charge 1, and we'll call this charge 2. So what's the electric field at that point? Okay, and one thing, they're both positive. So the electric field for positive charges, you show them pointing out. Okay, so at least in terms of that dot, that's really key to knowing the direction of the field. This is a positive charge, so positive charges are shown coming out. If this were a negative charge, the field lines would be pointing in. Okay, so let's get the electric field generated by charge 1. That's KQ over R squared. 9 times 10 to the 9th times 0.4 times 10 to the minus 3 coulombs. Again, it's millicoulombs over the distance is 0.4 meters, so to the dot, and that is squared in the denominator, and if you put that in your calculator, you get 2.25 times 10 to the 7th, and the unit is newtons per coulomb. Now the direction is really important. Again, the direction, since it's positive, the direction of that electric field is, the field lines are pointing out, so it would be to the right. If that were negative, it would be the opposite direction. The field lines would be pointing in. Okay, for the second charge, 9 times 10 to the 9th. The numerator is the same, 0.4 times 10 to the minus 3. The distance, though, is much further, so this electric field will be weaker. And that's going to be 1.41 times 10 to the 6 newtons per coulomb. And the direction, the field lines for this positive are pointing out, or in terms of how this dot feels, let's use that terminology, that electric field, it feels like it's coming that direction. So the vector electric field is going to be the right minus the left. 2.25 times 10 to the 7th minus 1.41 times 10 to the 6th. So that'll be 2.11 times 10 to the 7th newtons per coulomb. Okay, so that is the answer to the first question. The second is, what is the force a 0.56 millicoulomb charge would experience at that point? What we're going to do is rearrange this equation. Okay, we know vector E, we know little q, it gave it to us in the problem. So if we rearrange that equation, we'll have the force is equal to the electric field times the moving charge. The electric field, we just discovered that is 2.11 times 10 to the 7th newtons per coulomb. The magnitude of the charge is 0.56 millicoulombs, and it's positive. Okay, and you would put the sign in here. If the electric field were negative, it'd be negative. If the charge were negative, that would be negative. But the force is 1.18 times 10 to the 4th newtons. So we got to use that formula as a shortcut, and we didn't have to do like we did with on your own problem 13.5, where you had to figure out the force coming from one, the force coming from the other direction, and go through all of that. Since we had the electric field, we could simply place it into this equation here. All right, so that takes care of 13.8. I'm going to erase if you need to pause. All right, 13.9 really refers to the diagram in 13.8. And it asks, what is the electric field at the midpoint? So we've got plus 0.4, plus 0.4, and the midpoint would be halfway in between, so there would be 1 meter. Well, what's going to happen is these electric fields are going to cancel out. They're going to be exactly the same, but the direction of the one on the left will be a field that is going to the right, and this charge will send an electric field that's going to the left, and because they're the same distance and the same charge, the electric fields will cancel out. So your electric field, the answer is going to be 0, since the charges have the same sign and magnitude. So we really didn't have to do any math. If it weren't at the midpoint, then it wouldn't be 0. If they had opposite signs, it wouldn't be 0. They would add to each other if one was positive and one was negative. But since they're both positive and we're interested in the midpoint, they're going to cancel. All right, that's 13.9. Okay, finishing up this chapter, and we're on page 6 of your notes. We're applying Coulomb's law to the Bohr model of the atom. So to remind you about the Bohr model of the atom, and this is figure 13.6 on same page 446 that we've been on. So what we're going to do is, with the Bohr model of the atom, we're going to assume that the electron has a circular orbit around a nucleus. And we know that's not true, but we're going to assume that. And we're gonna go back all the way back to chapter 7 and use the centripetal force equation, which is mv squared over r. And we're going to set that equal to the electrostatic force equation, which is k times q1 times q2 over r squared. And if we do that, we can figure out velocity or mass or radius or any of these unknowns. Okay, so let's read through 13.10 on page 448. And that says a helium plus ion has 2 protons but only 1 electron. If the orbital radius of that 1 electron is 1.3 times 10 to the minus 11 meters, at what speed does it orbit the nucleus? Okay, so we're going to set the centripetal force, because we're assuming a circular orbit of the electron, equal to the electrostatic force. So we've got mv squared over r is equal to k, q1, q2. And in fact, let's not call it q1, q2. Let's call it q of the electron and q of the protons over r squared. So one of the r's is going to cancel. And we're trying to figure out the velocity. So doing the algebra here, the velocity is going to be, since it's v squared, we'll bring that mass underneath. So we'll have the square root of k times the q of the electron times the q of the proton, or the charge, over mass times radius. So this is a bunch of numbers we're going to be putting in here. All right, k is 9 times 10 to the 9th. It gives you that the charge of an electron is negative 1.6 times 10 to the minus 19, but we don't put the sign, so you're just going to put 1.6 times 10 to the minus 19. Helium has 2 protons. Okay, so we have to add the charge of each proton together. Well, a proton has a 1.6 times 10 to the minus 19 coulomb charge, but since there's 2 of them, we need to double that. What I want you to do is in your notes there, make sure you do 2 protons. Because some of your problems will just have 1, some of them may even have 3 if it's a lithium ion. The mass, okay, it's the mass of the thing that is doing the moving, which is the electron, and that is 9.1 times 10 to the minus 31 kilograms. Basically is massless. And then the radius, atoms are small, so they don't have a very big radius, 1.3 times 10 to the minus 11 meters. So that's a lot to put in your calculator, and then you got to take the square root. After all that, take your time. Maybe you just put in the numerator, write that down, put in the denominator, write that down. Go ahead and divide them, and then finally take the square root. One easy way to take the square root is just raise to the 0.5 power if you don't want to use that square root symbol. But if you do all that, and I want you to practice this in your calculator, you should get 6.24 times 10 to the 6 meters per second. Pretty fast. But there's a way to check this answer to see if your answer is sane. You know that nothing travels faster than 3 times 10 to the 8th meters a second. If you had forgotten to take the square root of this quantity, you would have gotten something bigger than 3 times 10 to the 8th. So that's kind of a check you can do. Make sure your answer is less than the speed of light. If it's not, you probably made some sort of calculation error somewhere. Okay, so you can finish up the practice problems based on this lecture. You should be able to do the second part of number 5. You can do number 8, and you can do number 10. So that finishes up chapter 13. And have a good day.